Yeah, recording is started, sir.
Okay.
So we are delighted to have you all of you join us this evening. So, and allow me to introduce our distinguished speaker for this evening, Dr. Anantharaj Vanaraj, a design verification leader for GPU hardware at Samsung Austin Research and Development Center and Advanced Computing Lab. He is based on San Jose, California, and is an active member of the IEEE Santa Clara Valley section, making it truly special to have him with our Bangalore community tonight. With over 20 years of experience in CMOS VLSI, NAND flash memory design verification, he has previously served as a director at Western Digital Technologies, leading verification across 10 plus NAND tapeouts and mentoring teams of 35 plus engineers. He holds a PhD in quantum dot cellular automata, is a senior member of IEEE, fellow of IETE and BCS, FUSA certified, and a proud recipient of the Scientist of the Year 2024 award. Please join me in warmly welcoming Dr. Anantharaj to take over the floor. Over to you, sir.
Thank you. Thanks, Chandrika. Thank you all for joining. I know it's a Saturday evening. I appreciate you joining, and it's Saturday morning for me in California. So I think the talk today, what I'm going to share with as a part of this industry insight series is the functional verification, which is one of the most overlooked and underwhelming contributions from the industry for a long time. Right. So people talk about the design challenges. People talk about the technology node challenges. People talk about the productization of any features coming in, any new technology, but always the function verification kind of overlooked. So today I'm going to talk about why it is important, why it become more complex. So it become a crux of the problem of the design flow or any chip design. And then what are the engineering crafts or the tools available? Right now, the industry is working on it, what it is using, very high level. So that's my uh, topic overview. Uh, my slide, everything, audio, everything is clear, correct? Shall I go ahead? Any feedback on that?
Yes, sir, it's clear. Please go ahead.
Thank you. So, disclaimer, like I said, my thank to everyone who has provided the contents in the openly available source. And all the purpose of this discussion is only for an educational purpose. Being part of IEEE, I always have this opportunity to share some of the industry insights of what we think about the functional verification, what are the challenges we are seeing. And this material, I think, apart from IEEE section officers, I think I recommend other people not to distribute or share it. Okay, so there is a basic exposure if you have on all these three or four things, it's okay. And if you don't have, is also okay. I'm not going to give a lecture today. And like I said, like Chandrika introduced me, I'm in the industry, so I know how important our time is. I know how important it is to make it efficient. The communication is right. So I will try my best to make sure this discussion is informative, than look like a lecture. Right. Okay, so getting attention is difficult, especially in the era of social media now with AI-based chatbots coming in. Nobody has to do anything. Everything is done by the machines. So it's very difficult to get an attention from each one of us. So I try my best to get the attention by making it simple, right? As simple as possible. That's why I always like this famous quote from Albert Einstein, right? So I'll try my best to make it simple, but feel free to ask me any questions on the floor. You don't have to wait till end of the discussion. Please feel free to stop me and ask question. So try your best to get that in, give the attention to me. I'm also trying my best to get the attention during the course. Okay, so I'm going to talk about this topic in this 5 sections. First, I'm going to bring about very high level idea. What is this functional or logic verification, and why it become very important? Right? I think if you talk to some of the folks who have been in this industry or the VLSI domain 10, 15 years back, I think verification is part of the design. It used to be an extended capability or extended task of design team, RTL design team. Things have changed a lot, right? And how it become crux of the design problem, right? I think people always talk about the Moore's law, but I want to talk about the Moore's law for verification. So I have a couple of slides on it. How it become a crux, correct? I think why people are concentrating more on verification nowadays, either resources, either in terms of the tools or the advancements happening. If everything comes and attack the verification problem, correct? And what are the tools, methodologies, engineering solutions available? And last but not the least, I think nowadays anyone is going to give a tech talk, we need to talk about AI because AI is changing the way things has been handled. Correct. So I'm not going to shy away from that. I'm going to share very high level idea. Correct. Like I said, I'm not going to give a lecture. It's more about an information session to create an interest and awareness about functional verification. Okay. Thank you. Okay. So what this design verification engineers or functional verification engineer or verification engineers in the VLSI front end design side does, the job is very simple. You catch the bugs what missed out by our counterparts, the designers. Correct. So I always say designers and verification engineers are partners in crime. So designers implement a feature for a particular way the design should work. Verification engineer is going to verify the feature by verifying what are the scenarios the feature should not work. Right. Between these two, it's like a Venn diagram. Designer think about the area covered by the chart. The verification engineer has to think inside the chart and outside the circle. For example, if you look at the Venn diagram, right? So think that way. So it's just catching the bugs. The bugs are nothing but an RTL design gaps or RTL design typos or the conceptual errors there, right? Oh, this is just a fun part when I training to freshers from the fresh out of the campus. Many of them is not aware how significant this verification stage is. So I used to use this example as another example to say that hey, the design is with rough edges, so we beautify it, we make it a better place, jokingly. So that's the idea. So keeping those things aside, I think what is actually the functional verification is making your design and design intent the same. You have an RTL design, you have a spec. We'll make sure whatever aspired in the spec by the architecture team, it is captured and implemented in the logic design or RTL design, correct? So when you implement, the process gets changed, right? So that's where the implementation in RTL, actual intent in the spec, we compare it. That is what logic verification or functional verification is, very high level, right? And please understand this is the front end design. And today, for our topic or our discussion today, I'm going to stick to digital design. I'm not going to talk about the analog mixed signal design or any physical design verification. So it's a front end design verification for RTL. Okay, so everybody knows about this, the flow, the chip design flow or the VLSI flow. It's a very complicated, long, lengthy process, I would say. So our topic of logic design verification is stuck in the front end design, close to the RTL, before the synthesis stage, right? After synthesis, it become the physical design. We are not talking about physical verification again, or we are not talking about LEC check or the RTL to netlist verification. We are talking about RTL verification. After the RTL is implemented, we just confirm, we take the responsibility of confirming the design is as expected before it gets synthesized. So we are at this stage, the functional verification. And the verification, there are different flows, but I just brought a very high level one. There is a test plan, test bench, coding the test bench, running a simulation, look at the simulation results, the coverage. There are a lot of tons of metric. If you talk to anyone in the industry, from every company or within a company, every BU, the vertical product line, everybody has their own metrics, the approaches to handle the verification challenge. It's very subjective and customized. Right. Okay, so before I go to the next section, anybody has any comments, questions? Okay, thank you. I'll go forward. Feel free to stop me anytime you want. So we talked about this in the couple of slides. I kind of give a very high level idea about the logic verification or functional verification. And the next question or the next area I want to create awareness is why suddenly it become key. People talk about architecture, design challenges, the synthesis challenges, the physical design challenges. PNR has been as still always a headache. are a very challenging environment, how the TNA team struggle at the last minute to get it completed. And then when the silicon comes, the silicon evaluation team, the post-silicon validation team, emulation team. So these are all very challenges. I agree. I think nothing taking away from those activities. But on the front end side, now the functional verification is became already a big challenge or more complicated challenge than the RTL design. That's what I'm going to bring out here. So why it is, right? So what's happening in the last decade or so? It's not something recently. It's been more than a decade, right? When I started my career, uh, it was more about design. Verification is a step in the design before we move it to the synthesis team, correct? And then when we ship our GDS2 to the fabs, I think there is a checklist where just there is one line about verification done, yes or no. That's all. RTL verification done, yes or no. But things have changed a lot now. So there is the from the chip design perspective, we are looking at chips capable of hundreds and thousands of features, and then it's keep on increasing. And the PPA metrics are really challenging, right? So the power, area consumption, performance, we are keep on demanding more and more from the electronics, the hardware circuits, which are getting demanded from the software applications. So it's a kind of cascading effect, correct? But at the same time, if you look at it in the industry, I think if somebody, excuse me, some any of you from the industry, you just compare your current generation of the product, what you're working, current chip design, chip we are working to the previous chip. You look at the schedule. Schedule would have been already compressed. At the same time, there are more features added. The performance metrics are higher than what we had in the past. So time to market is a key now, correct? Competitiveness. It's a cutthroat competition in the semiconductor industry. Not only in the industry, not only in the private sector, even you look at it from the perspective of geopolitical situation, the governments in every country is investing more and more in semiconductor. So uh, I don't know if you remember, there is a book called Chip Wars. So look at it, people are saying that is the third world war. Correct. There's a book from a professor in US, Chip Wars. Please, when you have time, read it. It's very nice. Correct. So that's what happening now. Correct. So time to market, and then the area, power consumptions, the metrics, everything has to be lesser than what we had in the past. So all these things, correct. When you demand more features from a design, when you want to get a better performance, at the same time you want to do it in a shorter time, all these factors are putting pressure on the front end side. So if you recollect what I mentioned earlier about designer and verification engineer, designer is going to design a feature and he is going to ensure that how it should work. But verification engineer has to verify how it should work, how it should not work. So that's where the verification complexity is in an exponential growth, right? So when you look at it, it is a study uh, it, from McKinsey and company, correct, where they're talking about in terms of the chip design cost, correct? First chart, this one, from the terms of nanometer, let's say right now, 5 nanometer design is going to cost almost $540 million, right? But keep that in mind. This is not only the verification cost. I'm talking about the entire uh, product design cost, chip design cost, and the NRE cost, everything involved. At the same time, how many man months or how many man days we need for a 5 nanometer design? We have almost 1,000 days we need from one person to do it. So why this is going up and up, right? So if you see this, there is a gradual growth or the increase happening from 65 nanometer to 5 nanometer in terms of cost, in terms of man days. So when you look at this, this is all coming because of there is various uh, stages in the chip design, which are like the architecture, the design verification, physical design verification, the prototyping, and then finally the software and application. That's what I'm showing you in this slide. I know it's a little bit old, but it still holds good. If you look at it for the 5 nanometer, the majority of the time and effort in the product design or the chip design went into the verification. When I say verification, this is the RTL verification. So this is one of the driving factor for the cost increase in your chip design, for the schedule increase in your chip design. So anyone can go and talk to any of the program managers. They always crib about verification because verification is always taking the longer time and most costliest affair, especially the front end design verification. Right. So that's what's an idea. So this is what based on our demand on how the chips has to be more capable, less cost, faster, earlier than what anticipated, what we want. So all these things putting pressure on the product design, which is indirectly impacting on the front end side. Front end side, the heavy workload has been shifted from designer to the verification. So that's what happening. Right. So this is, I know there are too much information in this slide, so don't worry. What I want to bring out is the complexity. The verification complexity is directly proportional to the design complexity. That's what I mean by here. So sometime in 1970, the processors has been designed by Intel or anyone were still talking about the Moore's law. Am I stepping up and catching up to the Moore's law? Sometime in 1980, we have all the six. Correct. The reduced instruction set came in 1990s, but before that, the six were there. Correct. Where people talking about, did we cross the Moore's law? Are we able to step up and match the Moore's law? But sometime in 1990s and 2000, all this advanced concept came in. Right. People talking about multi-threading, people talking about multi-core. So all these ideas coming in, low power design came in. So everything started changing. Right. So that's where in sometime in 2000, late 2000 to early 2010, people saying that, hey, the lunch is over, free lunch is over. So we have been riding on the wave of Moore's law, but we reached a point you can't downscale or scale down the node, right, in a transistor. So we have been increasing the computation capability by leveraging the Moore's law. Moore's law has reached a physical limitation. So we need to do something else. That's why people started thinking about multi-cores. And then now we are talking about stacking of codes and multi-threading whatsoever, right? So things are keep on increasing. Now we are in 2020, late 2020. Things are keep on changing every day, correct? So you will observe that. So all these things, correct? If you look at it, all this multi-core, multi-threading, as much as they impact the fabrication process, it also impacts the RTL design, because the RTL design is the brain of the chip, right? See, all other supporting components has to be there, but design is the one which controls how it should behave, the particular chip, right? So what is driving all this complexity increase in the design side? Obviously the applications, right? So like if just in the last 10 years, if you look at it, we talked about having the cloud infrastructure in the chip for the mobile phone to upload data, mobile phone to have more cameras, right? And then the memory capacity in memory computing, edge devices, the IoT came in, and then the obviously the network evolution, and then autonomous driving now, and then with the AI coming in, right? So beyond 2020, I know we are late in 2020, decade of 2020, right? So still things are catching up. AI is changing the way we are thinking and doing things in every day in our life. At the same time, the AI is not just a software solution. It's not like an application you can download and install. AI has to work in synergy with hardware, software, and the application, right? So that's where AI is also creating an design, or I would say that pushing and complexity challenge to the chip design, correct? The chip has to step up and contribute, correct? So that's what we are looking at. So all these things are making design verification more challenging, correct? But how it is becoming more tougher, correct? So when you look at these challenges, yes, I can add more resources to do, but at the same time, it's not about adding blindly resources. What's happening is there is a verification productivity gap, right? So what we can design, what we can fabricate, right? There is a big gap. That's what people talk about, this verification gap. How much of transistor you can design or put into a chip based on the feature size, the Moore's law, and then how much of those features implemented in those transistors can be 100% verified, right? So that is a big gap in the verification. That's what he called as the verification gap. You are not able to guarantee that all the features have been 100% verified. Similarly, in the past, we used to have this design gap. So people used to say that, hey, I can fabricate a chip with X amount of transistors, but you're consuming only X minus 10, because the design is not evolving. It's a challenge in the design, right? So all these things, if you remember, if you look at this 1980s, 1990s, the transistor level design to the gate level, as soon as it become gate level, we are not only talking about functional, the verification has to include timing. There is a timing verification. And then when the ASICs kind of application specific circuits came into picture, ICs came into picture, we are talking about not only functional, not only timing, we also start talking about the power. How much power is going to consume, correct? Whether my application is suitable for this kind of chip. And then the SARC came in. With the SARC coming in, reliability is a key challenge because we are putting system on a chip. It's not about one chip. If it fails, we can remove it, throw it, and replace it. That's not going to happen. The entire system is on a single chip. So we need to talk about making sure the functionality is verified at the front end, timing is captured, timing is verified, the power is measured, reliability of the entire SoC, everything comes into picture. And now we are talking about all this stacking, chiplet, wafer bondings, whatnot, correct? So everything is adding a plethora of challenges on verification as such, correct? The power verification across multiple dies, the timing across the die, system level connectivity, the chiplet to chiplet signal integrity. These are all not related to the functional verification, but I'm just talking about in general how it is becoming more complex. When you talk about all this capability, we are implementing certain features which goes into the RTL design. That's also increasing the demand on RTL design and the functional verification. So just to summarize, there is a gap, the verification gap, compared to what we can verify. That's why I call it as a verification productivity, what the chip can be, what the chip can contain, how many transistors can contain. Think that way, right? So yes, so I we talked about what is functional verification, why it becoming a key, and a couple of slides in the past we talked about how it becoming more challenge. And then the obvious question comes, hey, I know it's a challenging one, I know it's very important. What if something didn't go well? What happens, correct? So when the RTL design verification is a failure, let's say it is a bug, it got synthesized, it got fabricated as a chip, definitely there is a reputation impact, and there is a respin cost which is going to be in tune of $1 million minimum, and delay in the market, your product will get delayed, and then because your current product is delayed, the future project is also delayed. So it's a very demanding one, right? So unlike software bug fixes which can be released as a OTT or released as a package, software package you can download and install, that's not going to happen with the chip, right? So you need to replace the chip, you need to encourage the end customer to buy a new hardware product, right? So that's all going to impact how customers, consumers are going to view the firm, the reputation of the firm, correct? So it's very challenging. As you can see here, it impacts everything. The reputation, cost involved, how much of the capital spending you have to do, and how it's going to impact you at market positioning, how it is going to impact your future operation. So it's a nightmare, right? Okay, let me stop here. Any comments, questions still now? Okay,
Actually, in the chat box, Mr. Sajal has posted a question.
okay, good.
As technology node is scaling and new features addition or verification is exponentially increasing, what do you think? Which features or additional in verification methodology will keep the time under control and ensure tape out on time, except AI?
Yes, yes. Thank you. Thanks, Ajal, for asking that question. I think we'll keep aside the A. I'll come to that part. I will answer it in the section where I'm going to talk about the engineering crafts or tools, methodologies, what we have, which is helping us to make an timely tape out with an acceptable quality. Right. So I'll talk about it. Thank you.
Okay, thank you.
Yeah. Good. So let's talk about this, how it become crux of the design challenge. We talked about it. I just want a couple of slides to talk about the Moore's law for design verification, correct? I think when we started as a discrete component in a chip design, become multi-chip units, the microcontroller, CPUs, AC, SoC, and then all the chiplets now, there was a design complexity is continued to be there. It's still there, but at the same time, almost a 3x of verification complexity. So whatever you design, there is a 3x of time effort is required to verify that, especially on the front end design, correct? Because there is a thousands of complex features coming in, it's creating this verification complexity. That's what I call the Moore's law for design verification. At the same time, this productivity gap, what I talked earlier, I just want to bring it in a nice looking. If you look at it as of in 2020s, we are able to design the center one is the design graph, but we are able to verify only half of them. At the same time, we are able to design, but we are able to design only to the half the capability of the fabrication technology what we have, correct? So it's not about probably you might have someone might have a thought in their mind, oh, if you can fabricate, why not put all the multi, instead of 8 cores, why don't you put 10 cores or 16 cores in the chip if the chip has the ability to handle more? But yes, that looks easy to do that, but you think from the perspective of how the logic has to implement and handle a 8 chip core to an 16 chip core, how the complexity increases, how the power increases, the timing. So it's all complexity. When you put a design challenge, it complicate to the verification challenge. When it become verification challenge and design challenge, we end up not utilizing the final capability of the fabrication technology what we have. Correct. That's what the verification productivity gap. So today we are not talking more about the fabrication side. We stick to the front end design. Correct. So this is an interesting study from the research group. Correct. So sometime in 2022, when they had this analysis, they looked at what are the common factors, the reasons why an ASIC project in the industry is missing the schedule. Correct. So when they looked at it, most of the time it is, or I would say 66% of these projects are behind schedule, right? And 27% are behind schedule by 30% or more than that. So it's very alarming, right? So the next information is coming is why it is happening, correct? So when I say they are missing the schedule, it's not just because of the design or the fabrication. Majority of them are because of the respin. The respin is where you are redoing the entire chip again. When you do a redo an entire chip, there is a huge amount of cost involved. Excuse me. But what are those different factors, correct? As you can see here, excuse me. So if you see here, the logic or functional verification or the functional feature, that's what contributing to more than 50% as of 2022, right? It was always like that, almost 50% even in 2016, right? So it still continued to lead the pack, but there are clocking issues. That's why you hear about a lot of clocking verification, analog design verification, the crosstalk power issues. So there are different things, but we are concentrating mainly on this logic or function verification. So you're looking at respinning your chip, which is going to cost you millions of dollars, impacting your reputation of the firm, time to market, and your future product line. And why that is happening is 50% of that root cause is with verification or the functional design. So obviously the industry is putting an effort to make sure the verification is done to the highest possible quality. And that's why you see there is more hiring in verification in the last decade. Lot of designers are becoming verification engineers. That's becoming very common. So I started my career as a designer. I become a verification engineer. I'm sure it's still happening. And lot of the hiring right now, or the emphasis when you're building a design front end design team, there is always a 1:3 ratio for designer to verification engineer. Right. So that's what's happening. That's what right now, this is one of the way we are trying to solve this functional verification challenge by adding resource. Correct. So if you look at it, it's not only about resource. Yes, we can put resource, uh, but if the resource requirement is, let's say, 100 designers, then you need, for example, 3,000 verification engineers. It's not going to happen in real time. It's not in reality, correct? So what are the other things that are happening? So apart from increasing the headcount, apart from increasing our awareness, what's happening in the industry, right, which is helping us to achieve the tape out, right? Like the question what Sajal has posted, the functional verification quality or the ability to tape out your design from the functional verification, the front end design perspective. There are certain requirements in the sign off. Uh, or say tape out checklist we have from the synthesis team, PNR team, the power team, everything. But when you talk about functional verification, what we have, right? I think I use this to show that, right? I think I don't know how many of you correlate to the visual code checking. So those days, there were days where people manually will write or design the transistor, verify it manually by looking at it. There is no simulation, right? It's just simply looking at it, writing in a pen and paper, confirming it. This is what I'm planning, right? And then things changed. Simulation came into picture, right? I think nowadays simulation is like a right of way for someone who is doing design verification in the front end or anywhere, correct? And then many times in the past we used to look at the waveform, confirm it is working fine. Nowadays, most of the engineers, designers, verification engineers, they look at the waveform if something is failing. But those are days when we look at the waveform to confirm it is working fine. So things are evolved, correct? It evolved to a situation or a stage where we have this constraint random verification. The standardization or the accelerator came up with system verilog. become an IEEE standard. Then we reached a point where there are a lot of assertion-based automation checkers were there, and then methodologies came like OVM, AVM, VMM, then right now UVM, a methodology built on IEEE standard, right? So those things start helping us in terms of avoiding the eyeball checking, avoiding the simulation-based verification, concentrate more and more on automation, constraint random verification, trying to achieve all possible test scenarios, correct? And then we are at a point of inflection where this formal verification and AAML solutions are coming in, correct? Formal verification, who has been in the industry, it's been there for a long time. Static formal verification, especially LEC, is used always after the synthesis. But this formal verification is shifting the verification capability from the LEC kind of scenario into the RTL design, correct? So where we use the mathematical algorithms to prove or disprove how the design is working. We don't have to write test. We don't have to write any test bench. We don't have to write thousands of codes using system Verilog or UVM. You write a simple assertion and tell the tool to verify it on a design with certain constraints. That's all. The tool will go and explore mathematically and then come up and tell you. So those capabilities are coming already in the market. It's getting leveraged. The AML solutions, there are plethora of options we have, right? And that's rightly. I'm 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 very happy to see that the AAML or the AI as a technology is attacking functional verification in the chip design more than anything else. If you look at, go around, Google it, what are the EDA solutions for combined with the AI capability? Majority of them are targeting the functional verification. That shows how important it is for the EDA tool vendors, for the industry, and for the engineers. You think about an engineer who is working in visual coding, or someone who is doing this AML based solution to quickly verify the design and then move to the next project, correct? That's what happening. So this is the kind of evaluation we are seeing. I'm sure it's going to happen, continue to happen. Already the agentic AI stuffs are there, which are doing the entire verification by itself. So that's a separate topic, right? So we talked about this evaluation, not about increasing the headcount. We need crafts, the tools. When you think about the tools, we are seeing the evolution of the verification as a concept is evolving. And for this verification, what are the approaches, correct? I kind of lightly touched based earlier. The dynamic or simulation based verification, you have thousands of line of code written. Simulation based verification, it can be used for full chip, module level, or the IP reference modeling assertion, different components, correct? And there is a regression, automation, coverage collection. When you come to the formal, it's simple, straightforward, but heavy dependency on the tool, the engines in the tool, mathematical proofing, but it's going to take long time. Sometimes you stuck with bounded proofing or inconclusive proofs, correct? These two are very broad level, either by simulation or without simulation. But at the same time, the other approaches for functional verification is depends on, are you going to deploy the constant random verification? It doesn't matter whether it has to be UVM or even before UVM, we have system Verilog, directed random test, reference modeling, based automation, checking everything. Assertion based verification, correct? Assertion based verification used to happen as independent verification. Assertion modules, the checker models, there is an assertion coverage. And then coverage driven verifications. With all this capability coming in, we realize, hey, I'm going to run a random verification. I ran it for 3 days. So what is the coverage? What is the uniqueness of how many bins you hit, how many cover groups you're able to achieve? What is the code coverage? How much of regression, redundancy you avoided? How do you signed off? Those things. And then formal verification, obviously, what we talked. So all these things come into picture. The headcount increase is the first thing has been addressed by the industry. That's why you see every organization, every company almost hiring 1:3 ratio of verification engineers compared to design engineers. And then the evolution of verification as a concept, and then the evolution of all these approaches coming into picture, right? Now, with all this, we have the human, the resource available. We have all these concepts or the approaches readily available. Now, we need tools, we need methodologies, we need languages to implement them so that it can, the functional verification can be improvised. So that's what I'm going to talk in the next, in this 4 subsections, correct? As a language, as a metric, as a methodology, and what we are seeing from AI driven, right? So this is what has been happening in the industry, which is helping us to tape out on time with an acceptable verification quality, to answer Sajjal's question earlier, right? So Any comments, question? This will be my last section.
Yes, Girish,
Hello,
go
I
ahead.
have a question here.
Yes, please.
This is about a slide on the respin. So
Yeah.
you showed a graph on.
Yes.
So my question is it not possible to reduce the chances of respins because that's because of mainly because of the design issues, right? By improving the process of designing itself. What I
Yes.
mean to say is that, hello, can you hear me?
Yes, please, go ahead.
Yeah. So if you have a strong process for any design, that like mandatory guidelines, which
Yes.
every engineer has to follow.
Yes.
So it's just like traffic rules. If everyone follows traffic rules, there won't be any accident.
Yes. Yes.
So just like that. So if you have a strong set of rules which every engineer has to follow, so irrespective of the competence or the knowledge of the engineer, still you can get the fairly consistent design. That is what
Yes.
is my
Yes.
observation.
No, that's a good point, correct? And it's a good observation. And thanks for asking this question, correct? I think I just want you to take to an generalized concept, correct? As you mentioned, traffic rules, correct?
Mm.
It's anybody can come up with an excellent set of rules and regulations, but it's up to the people how to adapt it and follow it. Correct? We all know the chaos of traffic, correct? So we have all
Yeah.
the traffic challenges, correct? When the demanding is, it's I'm not saying that we are not following the traffic rules. We are following, we have been following, but we are reached a point where at the point of influx where it's too difficult to follow the rules strictly. So everybody start violating it. So that's the kind of thing is happening. Industry is having a very strong coding guidelines, code optimization, how to implement, how to reuse the designs, correct? But
Yeah.
the amount of time and the complexity of features coming in, it's putting unnecessary pressure on the designer. And I'm not saying the designers are making uh, this 50% mistakes consciously or because they don't have time. They are, most of the bugs are very difficult to think in human terms. The complexity. Think about a simple thing, correct? Like let's say you take a microcontroller, correct? There are
Mm.
thousands of code instructions, correct? All these combinations, how it should work, how it should not work. It's humanly impossible to think and verify by manual approach. So when they are designing, I know designers are getting beaten up whenever we see a bug, but the credit goes to them because they implemented the feature where it is working for 99% of the time. Only that 1% or that one scenario, it fails. Unfortunately, that's where the design, the chip design flow, correct? We have to respin. Otherwise,
Mm.
we are doing without chipped respin, we are doing concepts like disabling the feature, or we just mask that feature away to avoid that particular path of the design getting used. So all those capabilities are there, but this is more like an worst case scenario. If you have to respin. So I agree with your point. There are rules and regulations very clearly defined, right? Like ISO standards, we can put it. It is being there. Every company, every organization, and IEEE has lot of recommendation what to use, what not to use. But they are all coding. But when the coding converted into an implementation, when a
Mm.
person is implementing a case statement compared to an if statement, so there are bug escape when the person implement it in a case statement or if statement. The same feature, when you try to write it in a if and a case statement, there is a difference, correct?
Mm.
The scenario
Yeah.
changes, correct? And you can't anticipate that when you're doing an RTL design. And then when the designer comes, we are putting all our effort to think beyond that. Okay, like I said, the Venn diagram, how it should
Mm.
work, how it should not work. All this has to be put together and verified. But again, verification is also bounded by the project timeline. So
Mm.
many times, verification engineers are beaten to give the sign off go ahead, correct? And that's why, if you recollect, I'm always saying that we were tapered with acceptable verification quality. It's not my highest confidence. It is the moderate acceptable confidence. That's what happening in the industry till now.
Okay.
Any you say, can you close your eyes and say that you verified everything? Always there is a possibility of bug escape. That's complex it is, correct? Simple thing.
Mm.
Otherwise, you look from the theoretical perspective, correct? So what is verification is you take a digital design, it has 5-bit input. So 2 power 5, 32 possible combinations you have to verify. You take a 100-bit input, 2 power 100 possible
Yeah.
combinations. You think about all this SOCs coming in, complex interfaces like PCIe, CXL, memory requirement, processing capability, all these are blowing it out of proportion, right? So engineers are doing the job, tools are there to help us, but still the challenge continue to increase, right? It's a moving target, right? Hopefully I
Yeah.
tried my best to answer your question, but that's
Yeah,
a
yeah.
good observation. I like it, the
Yeah.
way you brought it in.
Okay, okay.
So,
Okay,
so
thank you.
Anantharaj, this is Karthi. I have one question. So I think that you have the data where the ASIC verification versus SOC verification. So when you go to SOC, you have all IPs and VIPs, right? So why, when we go to SOC verification, the verification, whatever productivity is kind of lower compared to ASIC? That part I don't understand. Meaning,
Okay, sure, Karthi. I try my best to explain to that,
yeah.
correct? So uh, the aspect what I'm coming from is, so you think this way, correct? There are uh, individual problems. There are 4 problems in your hand. Each of the problem you're working independently, so you're able to attack it and solve it. Assume that way, right? So once you individually handle all those problems, you're able to put a dedicated resource, time, attack it, solve it. But all those problems combined together, there is an interdependency between problem 1 to problem 2, problem 3, and problem 4. All this interdependency, complexity added, that's what happening. With SOC, all these IPs are verified independently. When they bring in together, they have all this interconnections, interfacing between them, timing between them, functional handshaking between them, everything added together. SOC verification has its own paradigm of expectations. So that's why I'm saying with SOC verification, the verification productivity is definitely a challenging one. The gap is increasing. That's what I mean. Independently verifying, combining together, when you're verifying, you're seeing new scenarios. Your requirement is more than what you did as an IP verification. That's what I mean by that, right? And with SOC, as the name indicates, with the entire system coming on chip, you're not simply verifying an AC for a particular application requirement. You're talking about system level handling. When you talk about a system, it is supposed to support or handle multiple applications. So SOC is more than uh, multiple versions of ASIC inside a single chip. So all those features coming in, all those requirements coming in, making the SOC verification more challenging. So that's what I meant by that. Uh, does it make sense?
Yeah, yeah. So what you're saying is your handshake between all the IPs is where your most of your verification time goes, and the
At
IPs
the
might be
SOC
very
level.
slow.
Yes, at
Yeah.
the SOC level. So when you when you look at any SOC design team, there is an IP verification, there is a cluster verification, there is a full
Mhm.
chip verification, and then there is an integration team, there is an integration verification team, right? So
Yeah.
integration in those days is simple. You just instantiate one RTL module, another RTL module, correct those 2 ports. But that's not the case nowadays. You have to think about how it is going to impact the place and route when I have this kind of 10 ports connected to another 10 ports in this SOC between these 2 IPs. So we have to think everything, right? So handshaking, interfacing, and how this feature is getting translated from one IP to the other IP. Because we are in a world where everything is, I would say, heterogeneous, correct? Multiple things are happening in a same chip. Those days are gone. Those days we have all discrete components. One ASIC for this purpose, another ASIC for other purpose. Everything is coming to SOC, right? So that's what the other aspect of complexity.
Got it. Got it. Thanks.
Yeah. Thanks, Karthik. A good question.
Yes, we have 2 more questions, Anantharaj.
Yes, please.
Lakshman, please go. Lakshman?
Oh no, I just have comments about both what Karthi and Girish has
Okay.
told. Maybe I will keep it to the end once Anant completes.
Sure.
Sure,
Yeah.
sure,
Okay.
sure.
Thanks, Anant.
Thanks,
Yeah. It
Lakshman.
was a wonderful presentation, Anand. It's very exciting. Yeah, please go ahead.
Okay, thank you. Thank you. Appreciate
Uh,
it.
we have one question in the chat box. Shoaib is asking, hello sir, how can undergrad student prepare to get into this exciting domain? Thanks for the wonderful presentation.
Oh, thank you. Thank you. I know I kind of consciously not touch based upon. It's good you're asking that question, correct? Uh, I'm a firm believer of basics is important. So please make sure If someone is aspiring to get into this verification, front-end design verification domain, concentrate on digital design concepts, concentrate on the entire VLSI design flow, and build your capability on all these languages, what I'm going to talk about, a Verilog, system Verilog, UVM, system Verilog assertions, and understand what's happening in the industry, right? So those things, and there are a lot of online free courses available about verification, and with this era of information is freely available. So concentrate on digital design, verification as a capability, well as a design flow. All these things will help you to get into or kickstart your career in verification. So just a very high level one. Okay, good. Any more questions or shall I go ahead?
This is just Javin.
Yes, please.
I was wondering was for verification specifically, like how do you verify the correctness of your test benches? Wouldn't like
Okay. Yeah, thanks,
This is-
Javin. That's an interesting question, right? It's
like
like
it's a paradox. Wouldn't
yes, it's a paradox, definitely, right? It's like asking someone, okay, someone is enforcing a law or a rule. How do you ensure that the person is following the rules and law, correct? So it's a very challenging one. So what you called as a test bench qualification, correct, or validating your test bench capability. So there are tools available even for that. I'm not talking about that today. There are tools which will take your test bench code and your RTL code, and the tool will automatically inject an artificial bug into the design and then see whether your test bench is catching. So it's going to explore different complexity, different scenarios, and then give a ranking for your test bench. So those kind of tools available. But you ask a verification engineer what I do by myself. So when I develop my test bench, I will also try my best to see if I tweak something in the RTL, that particular path by myself. You verification inject a bug and then see whether your test bench is catching, and that's one way of looking at it for to ensure test bench qualification. Apart from that, I encourage every verification engineer to be paranoid. Every verification engineer to be unhappy, disappointed if their test is passing. So when your test regression simulation is passing, you should be worried. That's what I encourage the designers, my team members to say. Look at it. Correct? Every verification engineer should be paranoid, always thinking that there should be a failure in the design. How come the design don't have an issue? If your test bench is not stepping up to that level, you go review the code. So all those things, correct? So just coming back to your question, Javin, I'm digressing. Sorry for that. Test bench qualification. There is a code review like how we do with design, RTL code review, system same way verification code review. There's an RTL spec architecture, same way we do a verification test plan. So these are all ensures that what you are doing, how we are verifying, the code review help us to catch issues, and then we depend on the industry tools and methodologies to help us. We are not missing any gaps in the test bench itself, correct? So, but it's an ongoing process. I don't have a single point to answer to that.
Okay. Thank you. Thank you for the answer.
Thanks, Javed. Okay, so like I said, this is my last section. So where I'm going to talk about the crafts or tools, engineering tools available, the improvements is happening in the industry to help the verification engineer, correct? So verification engineer used to get frustrated. I used to get frustrated in 2004-5 when I was doing my FPGA based design. So that simulator, that Verilog code to write it and verify. Think about verifying a design written in Verilog using the same Verilog, the same language. It's unbelievable. So you are limited by capability. That's where the languages came. Okay, so once the languages are there, we realize the part, okay, how everybody across the industry come together and say, these are the metrics. This is how I say verification is done. That's where the metrics came, correct? And then once the languages and metrics are there, people started doing their own way of doing it, correct? So it's very difficult between two companies. There is a company A buying an IP from company B. Company B is saying that I completed verification is this using this so capable language, all these metrics. But when they provide some data points to them, the company A couldn't understand what is the methodology, how they leverage. So then the standardization of methodology came into picture, right? And last but not the least, now this AI-driven solutions are coming in. We'll talk about it, right? So okay, so the language, I'm sure everybody knows about all these languages. And obviously from this, graph, you will understand that system Verilog is the most adapted one. So it's getting increased. Majority of the design verification is moving to system Verilog combined with system C and C++ verification. Correct. So Verilog is going down. VHDL is almost out of the picture. Vera is out of the picture. SpecMan has lost its edge. System Verilog, system C, and C++. Okay. So in this one, people may ask question, why still we are talking about C, C++, system C, right? Is there any common question? Okay. So
No,
why?
Anantharaj, only one question I have is why we are even talking about Verilog? Because if you look at the IEEE standard, there is only system Verilog and LRM right now, is that right? So why we are separating, I don't know, even this survey separately Verilog, I'm a little bit,
Yes. No, that's true. True. So we have IEEE LRM for Verilog that still continue to be there, and Verilog is still dominating the RTL design, not the verification, right? Almost 60 to 70% of the design constructs are still in Verilog. System Verilog constructs are evolving. The support for system Verilog in synthesis is definitely a challenge, but it has improved a lot, right? So why Verilog is still being considered as a verification? I I want you to think that from the designer perspective, most of the designers are comfortable writing Verilog test benches. Those are all sanity tests, the initial ramp up test. So those are still stuck to Verilog, and some of the legacy test benches are carried over. I'm not sure how many companies still use that. There are a lot of test benches which are written in Verilog. They just port from one project to the project and continue to do that. I think that's what added increase the this study, which contains the legacy test benches. Nobody is doing a new test bench development in Verilog. To answer your question,
okay.
majority of the people are doing it in Verilog. It's probably the legacy one, right? Uh, okay. So the C++ system C based verification is really important because I know I talked about this digital design, 2 per n possible combinations. You think about a scenario, there is an let's say there is an pipeline multiplier. It's still an RTL design. It's still a digital design. 64 by 64 bit multiplier with pipeline design. How difficult it is to verify using system Verilog based approach or even Verilog based test benches. It's going to be very complex, right? It's going to have plethora of, or the solution phase is very huge, and modeling it in system Verilog, make sure that internal pipeline stages are properly validated. These are all challenges. So that's where still there are certain complex functions they model in C++ as an reference model or as a simulation model. And then that model is used along with the system level test bench to verify the RTL design, which is implementing those kind of complex mathematical functions. Correct. So that's where C++ is playing a predominant role. But I think the question asked by, I think it's Karthik. So what's happening is new test benches are written in predominantly in system error. That's what the key takeaway from here. There are certain exceptions, right? So with these languages, things are improved. Uh, Verifying and Verilog design using system Verilog or even a methodology. I'll come to that, correct? So that has improved a lot of our verification deliverables, the ability to do verification, reduce the productivity gap for verification. So so this is about the metrics, correct? I know there are different metrics when you talk to anyone in the industry, but most of the industry is now agreeing with or going ahead with functional verification. For functional verification, the functional coverage, code coverage, correct? Any exclusion file, those kind of things is there. But when you look at metric to evaluate your capability, how well you did your verification, the test coverage, the code coverage, assertions or check coverages, and then constraint random verification, coverage driven verification, and then you come up with a test plan, make sure the plan goes around. So it's like plan, construct, execute, and measure. So this loop is going to continue every stage in verification. There are different metrics came up. People are using different metrics. So by creating different kind of coverage metric, we ensure that did we cover all those scenarios. By creating all this advanced verification capability, we are enabling the verification engineer to go and attack those coverages. within a shorter time, right? So before constrained random system Verilog test bench based randomization, we use Verilog dollar random, or at the best, the Verilog U random range. Oh man, think about it. You have to define all those random range for every random signal, and then make sure all the random values are get struck, get excited, verified, and then put a functional cover point for that, and then sign off. You complete your verification. But that takes lot of time and effort. Now with system analog based constraint random kind of test benches came in with the metrics defining in terms of coverage, the automatically the regression itself correct itself, go around and change the constraint randomization. When it is attacking X value, it knows it has to attack the Y value. The regression changes, the plan changes. All those things are happening. So that's what the metric driven. So we talked about the human resource increase, and then we talked about multiple languages coming in. Now, when the languages come in, this is an example about how the metrics has been evolving, right? So the next one is this methodology. I think recent past, I think last 4 5 years, people know only about the methodologies in verification. They never realized how much of evolution happened as a verification concept on the languages, the people hiring. So right now we are at the stage about this UVM, universal verification methodology. Long before that, we had AVM, ERM, VMM, OVM. Those days are gone, correct? So now most of the companies, I would say 90%, 95% of the industry is using UVM, and it has its own standardization in terms of how sequence is built, how sequence is reused, how the communication is happening. That's where we inherited the TLM from System Verilog System C environment, and then the database management, reporting is very obvious, very simple, correct? So when we used work in System Verilog based, we have to put all different kind of dollar display, dollar printf statements. All those things are gone now. UVM takes care of it. Register handling, register verification has changed, exception handling has changed, event handling has changed, a lot of things. And this is the uh, after system error came in, we realized how the race condition impacted verification also. Because when you write a code in Verilog, try to verify it with the same Verilog language, it goes through the same regions in the LRM, the language LRM, different regions, correct? Prepone, postpone, all those regions there. You think about the same constraint which is used to design, is used to verify the same feature. There is a race condition. Nobody know which one overtakes the other one. But with system overlay coming in, we are able to distinguish the verification code from the RTL code in the entire sampling region. So after that, when you have all this sampling, we know all these things are happening left, right. So can we phase it? We want to build the test bench in different phases. Make sure there is an compile, elaborate, and configuration, and then there is a reset phase. After the reset phase is done, you start your actual stimulus, and then the stimulus is completed, we shut down the design uh, empathetically, right? So those kind of things have been brought in by UVM. So that's methodology. UVM is one of the methodology, but that helped the verification engineers to think or come out of the limitations of constraint random verification. With methodology, we have a defined flow, right? That's what happening, right? So the last part, right? The AA solutions, correct? There are multiple discussions still happening, multi evolution is happening, but you think in terms of what AI can do for front end design verification. Anybody you talk to them, they talk about how to handle the design, how to handle the design verification in terms of coding, RTL design coding, RTL verification coding, and all about creating the test bench, how to make sure the test bench is proper, how to make sure the bugs are getting caught. All those things are coming in. So if you look at these challenges, there are violations, thousands of bugs when you do the manual analysis, how we can use the AML solution to handle it, how we can reduce the runtime. Instead of running your regression suite for 7 days, 10 days, how we can optimize it. We need help from the AI, correct? How to make sure all possible test bench configurations are captured in your verification. Different kind of root causing and debug analysis, different kind of coverage optimization. So everything, all these challenges are an opportunity for the AI-based solutions. That's what's happening, right? If you see this, so when I talk about all these things, it's not about automation. So please understand, AI is not an automation. If anybody's doing saying that AI is to automate stuff, that's not the case. Automation has happened long back with even with Python coding, correct? So this has been done. Now we are talking about how to replace the computing engineering effort, automate it, intelligently. That's what AI comes in, correct? Can we create an autofocus? Can we look at how to learn from all the previous waveforms that has been debugged? How to look at the spec and then identify what are the specific areas you have to verify? How to make sure the mathematical proofing in formal more intelligent? How to help the engineer in triaging? So failure analysis and triage is one of the painful stuff. You see a failure after 3 days of your regression, and then you take another 1 day to root cause it, correct? And root cause it to a point where designer can ready to look at it. All those challenges are there. That has been addressed by AI solutions, correct? So right from developing a spec, understanding a spec, doing and coding either for RTL design or RTL verification, correct? And then how to run the regression, how to make it efficient, how to make sure verification code, verification test bench is capable. We are not missing anything in that, the qualifying the test bench, and then how to intelligently optimize the way we achieve the coverage, we achieve the regression, how do we optimize the way we do the failure triaging. All these things are coming in AI solutions, right? So that's what my last slide, correct? I think there are I was very happy. I'm very happy to say that industry is using the AI predominantly for addressing the functional verification challenge. That's why if you go and talk to any uh, leading to a EDA tool vendor like Cadence, Synopsys, majority of their work concentrating on design verification, at the same time leveraging the AI capability for the other stages in VLSI flow. But still, verification plays a key role, right? So the Synopsys Copilot or JEDA from Cadence, all these things are bringing a different perspective to us. So when we look at it, it's definitely going to take a lot of our work from our side, correct? It's going to replace a lot of our contributions, correct? So those things are happening. VS4.AA for verification, design.AA for design optimization. Think about it, talk about it, look at it, correct? So all these things are happening. So it's good. It's happening in the functional verification. So at the same time, not only these leading tool vendors, there are a lot of startups, right? Chip agents, ChipStack, Moose AA, Bronco AA, Verify. I just listed few of them. Everybody is approaching this verification challenge from a different aspect. Nobody is competing in the same technology or the same solution. Their challenge is common. How to address the functional verification challenge, how to make sure the functional verification is complete, how to make sure verification can be completed within the schedule, how to qualify your functional verification is complete done, how to avoid respin, how to make sure you're able to bring more and more feature into the verification, into the design, thereby enabling verification, correct? So all this startups, all these leading EDA tool vendors are deploying AI and looks very promising. I've seen lot of demos. We are also evaluating something within Samsung, and I've seen a lot of other companies are doing it. They are very promising. I'm very excited for the next phase in uh, my career as a verification engineer. I'm looking forward to that. Okay, that's it. I know. Thanks for listening for the last 40, 50 minutes. Any comments, questions, anything?
Thank you, Anantharaj. I think we already crossed 1 hour. It's almost 1 hour,
Yes.
12 minutes.
Yes.
Sir, I have one question, please.
Yes. I'm coming to that, ma'am. So, Renuka ma'am has question. Well, let's go ahead with the question first.
Yes. Good evening, Anantharaj, sir. How are you, sir? I hope you remember last year we had one webinar with
Yes.
School of Engineering and
Yes.
Management.
Yes, ma'am. Nice to talk to you again. I really appreciate it. I know that was the UVM seminar, correct? I know we
Yes,
talked
sir.
about the
Yes,
UVM
sir.
there. Yeah, please.
Yes, sir. We had 400 plus participants, sir. All
Yes.
students.
Yeah. Yes, I remember
Okay.
that. It was a very, I hope it is very impactful. Students are getting their career into the verification. Yes.
Yes, sir. So today's session was very nice, and I have one basic question, sir. I just had a doubt regarding synthesizable and non-synthesizable constructs. Can you please clarify it, sir?
Oh, yes, definitely. Okay. So uh, synthesizable constructs, the constructs which are written in RTL code, when you synthesize it, they should become an equivalent circuit structure in terms of logic and gates, correct? So for example, synthesizable structures are always block, always with the
Okay.
passage of one, it will become a flop. without the passage or with level sensitive to become a latch. Think about initial statement. There is no equivalent digital circuit for initial statement. In Verilog system, Verilog, we have this initial statement, which is heavily used only for verification. You can't synthesize it. That is an example, very basic example. Advanced one, in system Verilog, we have concepts called semaphore. We use in UVM. We have mailbox. There is no way to
Yes, sir.
implement them, synthesize them into RTL structure. So that's what
Okay.
the non-synthesizable structures. Very few examples. I
Okay.
hope it makes sense.
Case and if, sir, you said about something, case and if statement, both are same. The
Yeah.
results, simulation results end up same.
Yes. Okay.
Then
So
how? Okay.
yes, yeah, that's the second part of the question, correct? So case statement and if statement, when I talked about this bug escape, I'm not blaming it on the designer, but how they understand that feature and implement it. So think this way. So if statement is a priority structure, case statement is an option structure. Case as an argument. If the argument matches a particular one, it will jump to the third or fourth option and match and execute. But that's not the case in if statement. If statement is a priority structure. You compare if statement with, let's say, option A first, else option B, else option C, for example. So A, B are coming high at the same time, but the if statement always execute the first part because the A is given the priority. So those kind of implementation specific, even though they understand the feature, the design feature thoroughly, when the designer decide how to implement it, that makes a difference. But they can't foresee that. Most of the time, they can't foresee that as a gap, as a challenge. Only the verification can bring it out. That's what I meant that.
Thank you, sir. I got clear understanding about case and if I was confused with this, and I thought it's similar. And simulation results end up in same, and even
Yeah.
the area, power, and the timing
Yes.
reports also give the same. So why we
Yes.
should go for why both
Yes.
are available? I had that question. Thank you so much,
Oh,
sir.
good, good. I think just to add that, I think appreciate it. The area will get impacted if you put default option in the case. You try it. Default will take
Yeah, sir.
away more area than anything else. So people are always worried about case because of that. And then
Okay.
case and if statement are different, but we can make them same. That's what System Erla came up with unique. There is a keyword called unique. I don't know whether you know about it. Please use that.
Okay.
Look at it.
Yes, sir.
Run unique.
Yes, sir.
Unique is a keyword before case, or use the synopsis pragma, full case, parallel case. These are all bring everything into the same plate and add more confusion. I'm just throwing ideas for you. You can run it and
Yes,
see
sir.
how
I'll
it is
try, sir.
impacting. Sure.
Yes,
Thank
sir.
you.
I'll try, sir. Thank you, sir.
Thank you.
Thank
Appreciate
you.
it.
Thank you, ma'am. Anantharaj, we have two questions and few
Sure,
comments
sure.
from watchmen. So I would request all the participants to stay back for 5 more minutes. I don't want to hold you guys over the weekend. We'll have a quick group photo and then we can close the call. And definitely you can talk to Anantharaj later, follow over the LinkedIn, etc. We have more questions.
Yes.
Vamsi, what do you suggest? Can we have a group photo first and then we can continue with it?
Yes, sir. That's,
Is that okay?
yeah, yes, sir. So before, just let me present the momentum.
Oh, okay, please.
Thank you, Anand, sir, for your nice presentation. And we're still having, we are ahead of the time. It's 9:17 in India, but we still are having the questions. And from IEEE CEDA Bangalore chapter and IEEE Bangalore section, a small virtual memento. Thank you again, sir, for accepting our invitation.
Sure. Thank you. Appreciate it.
I request everyone to switch on the cam so that we can take a good photo.
Please don't feel
I
shy.
request everyone to switch on the videos for a group photo. For a few minutes, I'll just lower all the hands so that it will align properly for me. Okay. On a count of 3, 2, 1. Thank you, everyone. So we can go for the Q&A.
Okay. I think we have one question from Daniel. Please, Daniel, go ahead.
Yes.
Dr. Vanaraj, can you hear me?
Yes. Yes,
Excellent.
Daniel, I can hear you.
Excellent presentation. But I noticed on several of the slides, there is the phrase credit to original content. I think that's a misunderstanding. You're not supposed to put the words credit to original content. You're supposed to put the actual credit to the original content in the slide. I only nitpick like this because I wanted to go to the original content for further education.
Yes.
And there's no reference slide at the end. That would be a welcome addition to your slides. Thank you.
Sure, Daniel. I'll take that feedback. I have a slide deck with references as a backup. I will bring that when I'm sharing it with the Sajal and the team so that we can all look at it. And I'll make sure to bring the links in the main slide itself.
That'd be wonderful. Thank you.
Thank you.
Thank you. Okay. Bala, please go ahead. Bala Murugan.
Yeah, hi, Anantharaj. So I am from TFT engineer. So in the session, I used to know functional verifications, how it's going to working in the industry. So I want to know one question here. Answer the actually you are doing coverage analysis, right? So with the constraints we are doing, right? So in these constraints, we are going to deliver as a pattern in the silicon, or how it's going to verify?
Okay, yeah, that's a good question. Thanks, Bala. I think from a DFT engineer perspective, verification looks different. So we are not, as a verification engineer, we are not generating patterns like how we do in DFT, the fixed pattern, random pattern. But here you think this way, the constraint, test benches, everything is written such a way that the tool generates its own patterns. The logic 0, 1s driving on the IO, all the IO pins of the design, it is randomly decided based on a particular feature or functionality we're verifying. For example, let's say 2:1 mux is there. When a DFT engineer is going to verify whether it's really working fine, you're going to decide 1, 0 here, the selection bit 1, 0, and then we'll make sure there is a sequence of pattern verified. The same thing, verification engineer do it in a RTL verification different way. What we are going to look at is there is a 2:1 mux, I have a selection signal. So I'm going to write a test saying that my selection bit is 1, my input on the input 0 should not propagate to the output. When my selection is 0, so like that we write in terms of higher level of abstraction. We don't write patterns, but we write test cases. We write test stimulus. They will generate the patterns internally. And there are a lot of industry solutions available, either open source or internal, where they dump this sequence, the patterns, and use it in the DFT. You can think about it.
Yeah. But I have another one question. So you will insert the fault to identify the test bench, right? So how you identify in the test cases? If you have made some mistakes into generate the coverage, so how you identify the test case is wrong?
Yes. Okay. So this is the same paradox question, correct? So when you talk about qualification of your test bench or test bench capability, so I give one example. We introduce by ourselves in RTL bug. And what if that RTL bug, for example, there is an RTL as an issue and the test bench also has the same issue? You can't catch it. That's unfortunate situation, correct? So that's why in the industry, we do verification at different level. IP verification, the block level verification, the cluster level verification, and then the SOC or a full chip verification. All these levels of verification will indirectly help us to weed out any wrong assumptions, constraints made at the IP, we should have caught in the block level. So we are depending on each other to catch it. But if everybody misses, definitely it's a miss and a respin. So that's very unfortunate situation.
Thank you.
Thank you.
Thank you. Shoaib, do you want to ask your question or should I go ahead?
I think Lakshman want to share something.
Yes, maybe we'll keep it Lakshman in the end as he suggested.
Okay.
Anybody
has any question?
Yes. Any idea what kind of AI approaches are being applied? Are frontier models like OpenAI, Claude being used or custom models being deployed?
Okay. So, like I said, it's very interesting time bringing AI into picture anywhere, not only in our VLSI design or anywhere in the industry. And you are seeing the amplification of AI in software world. There are a lot of headcount reduction, lot of change in the way how business is being done. So that is going to continue. But when you come to VLSI verification, especially the functional verification, the LLM models are heavily used to forecast a failure, debug a failure in a better way. For example, from the previous learning, let's say I debug a failure in a test case. I ran it after 3 days, there is another failure. So as a human being, my experience in the knowledge of what I gained 3 days ago, I'm applying it again when I'm debugging. No, the machine is going to do that. That is where the training comes in. So they're training all these learnings from all other past experience, other teams' experience, everything is convoluted. Those kind of models are coming in. And the obvious one is what is what, correct? And the obvious question, like I think today, the question from Renika madam about the non-synthesizable synthesizable feature, we have all the chatbots there. You just type it, it's telling you, and you just copy paste your code, put it there. Hey, I'm going to create a test with this code. Do you see any issues? You type it, it's going to respond to you. You're going to ask questions. Those kind of applications of AI coming. And the next level is the computing AI. AI is telling you what test you have to write to verify that feature. We used to do that as a part of our test plan review. We used to do that as a part of code review. Now AI is giving a heads up to you, right? And then AI is helping us how to run a regression. So when I say AI combined with all this LLM models behind that. So I'm not going to call out each and every company or the LLM model. That's not the correct way of doing it, but I'm telling everybody is coming up with solutions which are adding value in terms of verification, all the way from spec generation, code optimization, and then test bench development, test bench qualification, regression, coverage generation, debug analysis, triaging, and then the sign off or the verification closure. Everywhere we have one. And everything put together, there is an agentic AI, we can replace any one of us at one point of time. That's how it looks.
Thank you, Anantha. Okay, Lakshman, please go ahead.
Yeah, you are able to hear me?
Yes.
Hey, good evening, Anantharaj. I mean, it has been a wonderful presentation. I think like you have covered pretty extensively, comprehensively all the domains, but maybe the reason I want to take it towards the end is it has been a wonderful presentation. To start with, thanks a lot for engaging us with us. I want to add some complementary information here. Yes, definitely, I would like to start with what Daniel has pointed, to put the references rather than just original word, which anyway we have taken care going forward. Coming back to Renuka ma'am's comment, right? I just want to don't leave it like that, like saying, Renuka ma'am, like when you said case and if when they are simulated, I'm seeing the same results. If you're seeing the same results, that means your verification coverage is poor. Means you're not verifying all the possible combinations. If you verify all possible combinations as the input conditions, you will definitely see a difference. So,
Sir,
I
what
mean,
do you mean
that
by all possible combinations? Is it like 1 and 0 or all the other X and Z including?
all possible
We are,
combinations. I will just leave
we
it there
are
in the interest of
doing,
time.
okay.
Yeah, no, just
Yes,
1 and
sir.
0 is enough to just 1 and 0 is enough to without excess, but excess
Yes.
will also have a play. But even 1 and 0, not just the static combinations, sequentially how they appear, how the
Yes.
combinations appear, right?
Yes.
After 0 0, do you get 1 1 or 0 1 or 1 0 glitches? I mean, all kinds of combinations you need to
Yes.
look at. When see now the questions that is asked by Karthi about SOC verification, all that will become very easy. Simple 4 input if for case statement. When I say all possible combinations, including transient combinations and all of that, your mind is already it's blowing, mind blowing, right? When it comes to SOC and complexity, that is where the coverage has become very difficult. It will never be 100%, right?
Yes.
So anyone who says the simulation is showing the same results, fundamental problem is coverage is less. But we can discuss the details, right? Second,
Yes, sir.
when it comes to SOC, Karti's comment, like a little more on that. More than what additional aspect that we need to understand is the reuse, right? Unlike ASIC, where every component was in-house, built custom for the purpose. Now in SOC, every piece of IP, different IPs, CPU is coming from somewhere, memory is coming from somewhere, my JTAG IP is coming from somewhere else, my various memories, analog IP, each of them are coming from somewhere. And those vendors or third parties, or even in your own house, right? They're not building the system for your particular project. They are building a system for reuse for wider portfolio with a super spec right? And you're picking them based on your understanding that this IP is suitable for my SOC, and then you're integrating. So now how well you have, first of all, the spec verification, your integration, have you picked the right IP across all specifications, right? Is it suitable for your context? Are you not exercising the IP beyond its original capability? All these have to be checked, right? So that is where the SOC complexity goes up. And many times people underestimate the power of reuse and the challenges that come along with it, right? They think any reuse IP that has seen a silicon, oh, this is a silicon proven IP, I will go reuse in my next tape out, and I will do bare minimal verification, it will go through. It won't go through.
Yeah, got to.
It might have seen a silicon in a particular context of SOC integration. The next integration context is different. The verification has to be different, right? You have to make sure whether you have exercised all those scenarios, or have you, in the previous scenario, previous integration also, right? Those are a few aspects I would like to touch upon. And then when it comes to UVM, we talked about the coverage. Coverage is one of the important things. We just, Anant has briefly touched upon it, but it's a topic in itself, right? You can get into the details. But unfortunately, we only talk about digital foundations right now. When it comes to analog mixed signal, RF, on-chip power management, low power and all of that, many of these artifacts have not yet evolved. And in fact, like last year, end of last year, 2024-25, early, the latest system Verilog LRM has come out, which is having integrated all the Verilog AMS constructs into a system Verilog. Now, system, if you go to the latest standard, I was part of the committee. The system Verilog, when you take the latest one, you don't need to have separate Verilog AMS for analog modeling, right? Or analog behavior. Remember again, Renuka ma'am, whatever you write in Verilog AMS, anything on the simulation side of system Verilog and AMS side of Verilog AMS are not synthesizable, right?
Okay.
So they are only for simulation purpose and modeling the analog content and verification, but you cannot synthesize them. What is synthesizable is only the original Verilog. Somebody also asked why Verilog. Only the original Verilog part of the subset of system Verilog is synthesizable. Everything else is I'm probably exaggerating it, but that's how we should look at in a high level, right? And finally, when I come back to Girish's comment on traffic light example, right? So those are there to do right things. For example, the traffic light, traffic rules are there to keep the process seamless and avoid accidents, but it doesn't help you whether you've really reached where you want to go. That is up to you. That is your spec, right? So you have lint checks and other checks for writing. Whether you're writing only synthesizable subset of the code for the design, right? All those foundational checks do exist. They quickly give you results that what you have written will not go bad. But how does a machine know what is in your mind as a spec that you have converted into code? That is part of verification. That is what cannot be done, because today not every specification is written and machine readable. The machine readable specifications are your system Verilog test benches and test cases, and hence by construct right design today, current state of affairs, it's not possible. It may evolve, it may come into being. For example, when it comes to layout, it can check for manufacturability checks like DRCs, right? But if you have given a wrong connection, only LVS can check, right?
Oh,
DRC cannot check. Just some examples. I'll leave it there.
Okay.
Okay.
Thank you, Lakshman.
Thank you, Lakshman.
Very brief comment, because we touched upon AI. Because the code, in academics it's okay, but when it comes to industry, right? Even in academics now, copyright is extremely important. IP protection is extremely important. Remember, when you ask AI to generate a code, generative AI is dangerous. You may end up using somebody else's copyrighted code or section of the design that's okay for you to use, but you cannot commercialize it, right? Then you will be in a big legal soup. What I mean is, it helps us move forward fast, efficient, but be mindful of ethical aspects and legal aspects of it. And when it comes to, again, just because ChatGPT is a general purpose model, when it, as Anant has already pointed out, there are domain specific models coming up. You have to apply RAG. A lot of the other advanced techniques in AI you need to understand for you to apply them in a specific domain or specific area of interest for you in technically. It's not that I can pick up either ChatGPT or Gemini and then apply and then I will get good results. many times it will hallucinate. It won't give you any good results.
Yes.
Thank you. I mean, but thanks a lot, Anantharaj. I mean, I've looked at comprehensively the entire spectrum. Thank you very much.
Thank you, Lakshman. I think thanks for adding the insights from your side. It's good, right? I think I'm very happy Rananga Madam is trying a lot of things. I think it's good. You are exploring, thereby you're enabling your students, correct? I think we all wish that every student has a stop like that in our college, in our part of our curriculum teaching. Yes, correct. So please continue to do that. Really appreciate it.
Thank you, sir. Thank you so much.
Okay, I think let's not extend too much. It's late for India as well as I know a lot of stuff Anantharaj need to take care on Saturday. So over to you, Vamsi.
Sir, nothing much.
Okay.
Thank you, Anand sir, again. And good night, everyone. Happy weekend.
Thank you. Good night. Happy weekend. Have a nice day.
Thank you, Anantharaj,
Thank you.
again.
Yes.
Thank
Take
you
care.
everyone for joining.
And all the best,
Thank
all
you.
the students. Thank you. Bye.
Thank you. Bye.